Good day, everyone, and welcome. Thank you all for finding time and attending this webinar, Active Area of Heterogeneous Catalysts, Chemisorption and Temperature Program Techniques. My name is Jeff Kenvin, and I'm Technical Director at Micromeritics Instrument Corporation, a global leader in material characterization technology. I'll be your moderator for today. Our today's speaker is Dr. Luca Lucarelli. Luca is a Micromeritics Technical Application Consultant. Before we start today, let me explain how you can raise questions. If you have any questions on the content presented, raise them over the phone or write them to chat in our Q&A session at the end of the webinar. The webinar recording will be available on our webinar landing page, so make sure you check back in about 1.5 weeks, but you'll also be provided a link to the recorded webinar via email once available. At the end of the webinar, there'll be a brief survey. Please take the time, if it permits, to fill out our webinar. Now let's get started. I'm pleased to introduce today's speaker, Dr. Luca Lucarelli. Luca received his PhD in 1988 from Milan State University. He's been involved in material characterization for more than 3 decades. He's been instrumental in introducing techniques and instrumentation for the characterization of surface area, porosity, active surface area, and temperature program techniques. I'd like to now hand this over to Dr. Lucarelli to learn more about active area of heterogeneous catalysts, chemisorption, and temperature program techniques.
Welcome everybody to this second webinar about heterogeneous catalyst. Today we will have some deeper description of the available techniques for chemical gas adsorption in isothermal conditions and the dynamic methods used in temperature program reactions. We are going to focus on the two most used heterogeneous catalysts, supported metal and acid-base ones. Supported metal catalysts are constituted by an active metal dispersed on a high surface porous support made of an inert material. The metal and the support are designed in function of a specific type of reaction. Zeolites are crystalline microporous materials forming frameworks with up to 3-dimension pore networks ranging from 0.3 nanometer to about 1 nanometer size. Metal ions, silicon and aluminum, are linked through oxygen or hydroxyl bridges, generating acid sites on the internal surface. Bronsted acidity is mainly related to the ratio between silicon and aluminum, while the introduction of other cationic species like transition metal ions may provide the zeolites with the Lewis acid sites or redox catalytic properties. Let's remember some definitions related to catalyst. The following parameters are generally determined for fresh catalyst and after use. The metal percentage is calculated or measured by specific techniques like atomic adsorption and represents the percentage in weight of the metal in the catalyst at the production. The free metal surface area is the specific surface area of the metal active phase that is exposed to reactants at a given temperature, usually smaller than the total catalyst BAT surface area. The metal dispersion is the ratio between the exposed metal atoms and the total amount of metal in a catalyst. Strong active sites chemisorb the probe gas in irreversible way in isothermal conditions, while weak active sites chemisorb in a reversible way, that is, gas molecules are removed just by flowing an inert gas or applying vacuum. Active site concentration usually refers to the number of acid or base sites physically free to react. Redox sites properties indicate the reducibility or oxidation properties of a catalyst. These are bulk properties that can be evaluated usually at high temperatures. And finally, activation energy for desorption represents the binding energy of a probe gas molecule with the active site. Following some definitions related to catalytic process. Activity is the speed at which a chemical reaction reaches the equilibrium. It is also defined as the amount of reactant transformed into product per unit of time and unit of catalyst volume. Selectivity is the rate of reactant conversion into the desired products. Selectivity usually depends on catalyst and support nature, but also on reaction parameters like temperature, pressure, and reactants composition. Surface acidity and heat mass transfer in some catalytic conversions affects the kinetic of the process. Regeneration processes are very important to be investigated after testing in pilot reactors to evaluate the procedures to get rid of poisoning and fouling effects. Stability is mainly related to the catalyst lifetime when irreversible damages due to sinterization or loss of active sites occur. And finally, some effects occurring during the chemical reaction. Spillover is a phenomenon that involves the migration of a chemisorbed species formed on a first active phase onto a second phase that usually could not react if present alone in the same conditions. It increases the reactivity, but sometimes it worsens the selectivity. Often it is seen at high temperature and pressure. Sinterization is a migration of the supported metal atoms to form larger metal aggregates, thus reducing the metal dispersion and surface area. Sinterization is a direct consequence of temperature, time, and aging. Supports might be also subject to sinterization, blocking the access to pores. Poisoning is an impurity or a compound present in the fluid that selectively sticks on the active sites. Poisoning can be sometimes irreversible. Fouling, namely pores obstructing, may happen if the support is not properly designed for a given reaction. One of the products may obstruct the pore access, thus preventing further reactants to contact the active phase. Can be considered like a poisoning. Erosion is a loss of active phase during the use. It depends mainly on catalyst aging. Active surface and bulk reactivity testing can be divided by two main groups of experiments. For the active surface investigation, isothermal chemisorption and temperature-programmed desorption techniques, and for bulk reactivity study, we have temperature-programmed reactions like reduction and oxidation. In supported metal catalyst, it is essential to define the metal dispersion percentage because it represents the efficiency of the metal deposition process in fresh catalyst and determine the degree of deactivation with aging. Metal surface area, dispersion, and metal aggregate size can be determined by chemisorption in isothermal conditions and by temperature-programmed desorption. The active sites concentration is a parameter mainly related to acid-base catalyst and can be measured by chemisorption or desorption of molecules like ammonia or carbon dioxide. The adsorption energy of a given sample is measured by multiple TPD performed at different heating rates. Bulk reactivity tests like TPR and TPO requires high temperatures to activate also the metal in the bulk. And finally, the reactivity test can qualify the use of a catalyst for a given reaction, permitting the evaluation of activity, selectivity, lifetime. These tests require small-scale pilot reactors. The chemisorption techniques are very well established analytical methods to evaluate the free metal-specific surface area and metal dispersion degree. These methods consist in performing a real chemical reaction in isothermal conditions between a reactive gas and a catalyst that has been previously activated in a suitable way. The pretreatment procedure should be designed according to the required analysis. We can identify three main chemisorption procedures. Chemisorption of a probe gas with a surface metal according to a known stoichiometry. Titration of a surface metal oxide or hydride with hydrogen or oxygen. Again, the stoichiometry of the reaction must be known. Chemisorption of a basic gas like ammonia with a surface acid site. In this case, the stoichiometry is often unknown. The sample preparation has the task to bring the metal deposited on the support surface to zero oxidation state, commonly by a reduction process. This procedure activates the catalyst to chemisorption. In case of a titration, we need to oxidize the surface metal to promote the reaction with hydrogen, generating water. And finally, in case of acid-base reaction, the catalyst surface should be free from pollutant vapors and treated in a flow of inert gas at high temperature to activate the surface. The sample preparation prior chemisorption is extremely important, but not so easily determined. In this table, we report the main conditions at which chemisorption occurs. The gas and solid nature and the temperature lead to the phenomena of chemisorption or physisorption. Inert gases are mainly subject to physisorption at cryogenic temperatures. On the other hand, when an active solid, like a metal-supported catalyst, and a reactive gas are put in contact at a relatively high temperature, chemisorption takes place. The energy involved in this case is related to a chemical bond. Thus, a chemisorbed molecule gives place to a different surface compound. Chemisorption in principle may occur at any temperature, but the temperature range is specific to the gas and solid interaction. Also for this reason, chemisorption is highly specific, and sometimes it is irreversible if the product of surface reaction is very stable, like some metal oxides or sulfur compounds. It is important to underline that physisorption and chemisorption always coexist, giving place to hybrid situations like in the case of a reversible chemisorption. And finally, chemisorption in principle is limited to the formation of a monolayer, because once all the available surface active sites have reacted, there should not be room for other interactions. But in real life, this is not true, as we will see later. Metals used in heterogeneous catalysts have affinity for some specific gas molecules. Most common adsorbate for metal are hydrogen, oxygen, carbon monoxide. We must remind that the analytical instruments measure the quantity of a probe gas chemisorbed or reacted with the metal. Thus, it is very important to know the precise stoichiometry of reaction if we need the quantification of the surface metal atoms. Generally, the stoichiometric factors should be related to the metal. The correct choice of the adsorptive should take into consideration the following factors. It must react with the metal, should have a short adsorption equilibrium time, should show a minimum effect of adsorption in the support, minimal effect of gas-gas interaction avoiding the multilayer formation, minimal effect of gas dissolution in the metal, like for instance hydrogen and palladium, and possibly the stoichiometry should be known. In this table, some side effects are put in evidence, like the spillover of hydrogen over platinum at high temperature and the long equilibrium time for hydrogen on ruthenium due to spillover even at room temperature. Let's see in detail the most common adsorbates used in chemisorption experiments. Hydrogen is the most used gas for chemisorption measurements. It is frequently used to analyze platinum, rhodium, iridium, and the noble metals of the group 8. Hydrogen cannot be used to characterize silver and copper, and it forms with palladium a solution that is function of the temperature and pressure. Generally, hydrogen is adsorbed in a dissociative form, but many other mechanisms of interaction with active surfaces are known, like spillover, bulk adsorption, or dissolution and reversible chemisorption. Oxygen can be used with metals, showing easy oxidation properties. The disadvantage of using this gas is that oxygen might change the surface active structure by corrosive chemisorption. In dissociative adsorption, oxygen atoms are strongly bound to the surface and will tend to occupy the highest available coordination site. The strength of the interaction between adsorbate and substrate often causes the displacement of side metal atoms. On the reactive surfaces of metals from the left-hand side of the periodic table, the adsorption of carbon monoxide is principally dissociative, leading to adsorbed carbon and oxygen atoms to form surface oxide and oxycarbide compounds. By contrast, with the metals from the right-hand side of the D block, like copper and silver, the interaction is mainly molecular. The strength of the interaction between the carbon monoxide molecule and the metal is also weaker, so the metal-carbon bond may be readily broken and the carbon monoxide desorbs in molecular form when raising the temperature. For most of the transition metals, however, the nature of the adsorption is very sensitive to the surface temperature and surface structure. As the stoichiometry with carbon monoxide is uncertain for several metals, sometimes it is not reasonable comparing metal dispersion results obtained by carbon monoxide chemisorption with other gases having a known stoichiometry, like for instance hydrogen. Ammonia has a lone electron pair on the central nitrogen atom that is available for bonding. Ammonia may bond without dissociation to a single active site, acting as a Lewis base. Progressive dehydrogenation may occur to give surface NH species and adsorbed hydrogen atoms, acting as a Bronsted acid. Ammonia is used to characterize all Bronsted and Lewis acid sites, and being a small molecule, it can be adsorbed also in very narrow micropores. Acid catalysts are mainly used in cracking and hydrocracking processes. These type of reactions are performed in mesopores and large micropores. Smaller micropores will not influence the reaction because of steric hindrance of the reactants. For this reason, zeolites used for this task are subject to a demetallation process to increase the micropore size without changing the crystalline structure. Pyridine is conveniently used to characterize the strong and medium acid sites in larger micropores and mesopores. Chemisorption of Iso-Propylamine is commonly used for determining the Bronsted acid sites. It is less basic than ammonia, and when after chemisorption is submitted to a temperature rate, at high temperature a surface reaction occurs, dissociating the amine into propylene and ammonia. Summarizing, ammonia will measure the total Bronsted and Lewis acidity in all kinds of pores. Pyridine can measure strong and medium Bronsted and Lewis sites only in those pores that are effective for the catalytic reaction. And finally, propylamine can be adsorbed mainly on Bronsted acid sites. Thus, it is possible to measure the Lewis sites concentration as a difference between pyridine and propylamine adsorption. Methanol vapor is often used to characterize acid and base sites at the same time. The analytical procedure is more complex and involves two sequential experiments, as we will see in the next slides. Methanol chemisorbed on acid site undergoes to a surface reaction, producing dimethylator, while on basic sites it dissociates into carbon mono and dioxide. And finally, if redox sites are present, it will act as a reducing agent generating formaldehyde. The chemisorption techniques provide fundamental piece of information on the catalyst active phase. Depending on the technique, static or dynamic, and the adsorbed choice, we can quantify strong and weak active sites related to irreversible and reversible chemisorption. These parameters play a fundamental role in the basic characterization of a catalyst and in the evaluation of catalytic activity, selectivity, and in the study of the activation phenomena and consequent regeneration process. There are different methods to perform chemisorption. The most used are the static manometric and the flow dynamic method. In the volumetric method, like for physisorption, the sample is kept under high vacuum before the analysis. In the static manometric apparatus, the instrument introduces sequential known doses of reactive gas into the sample holder, measuring afterwards the absolute equilibrium pressure that will be established between the chemisorbed phase and the gaseous phase. Flow dynamic methods are carried out generally at atmospheric pressure, but can be performed also at high pressure with suitable instruments. An inner carrier gas is passing through the sample in a suitable flow-through microreactor. The detector can be a thermal conductivity detector, a mass spectrometer, or else. During the chemisorption process, the reactive molecules interact with the active surface, often according to two different types of binding, irreversible and reversible chemisorption. Irreversible chemisorption produces a stable chemical compound at the catalyst surface. Examples can be metal hydrides or oxides that are stable at the analysis temperature even when the reactive phase is removed. Reversible chemisorption is generated by weak interactions that might take place on energetically disadvantaged active sites or on an activated support. The bonds in this second type of chemisorption is very weak, and it is sufficient to remove the probe gas from the gaseous phase to break such light binding, desorbing the gas molecule. Other reversible effects might occur, like the phenomenon of absorption, that is a gas dissolution into the bulk metal, like hydrogen in palladium. The flow dynamic method in chemisorption usually fails to detect reversible interactions, as the catalyst is constantly submitted to an inner carrier flow. The static manometry technique can provide more information about the surface reactivity, but the experiment might take a longer time than the dynamic technique. In static systems, the amount of gas chemisorbed is measured at the real equilibrium, thus permitting to apply several calculation models to evaluate the different species of chemisorption. In addition, using specific procedures, it is possible to distinguish reversible from irreversible chemisorption and to put in evidence some other phenomenon like hydride formation or structural changes. These effects can be quantified performing a double chemisorption run involving a degassing phase between the two experiments to remove the reversible adsorbed molecules. The difference between the first and the second chemisorption corresponds to the irreversible chemisorption related to strong binding energy. Static systems need high vacuum, and the manufacturing quality is fundamental to avoid leaks that may affect the reliability of results. The sample activation procedure prior to static or dynamic chemisorption is generally the same, but the static method needs more time to complete the experiments compared to the dynamic ones. The dynamic method consists in flowing continuously at constant flow rate an inner gas through the sample in a microreactor. Then known doses of reactive gas are injected by a loop valve into the gas stream. When the reactive gas pulses reach the catalytic surface, the gas molecules react with the sample being chemisorbed. In case of dynamic adsorption, it is not possible to state the correct equilibrium time for the chemical reaction. Therefore, the only parameter that can be adapted to allow sufficient contact time between the gas and the solid is the flow rate. Using the dynamic method, the lower is the flow rate, longer is the contact time between the gas pulse and the sample, providing a situation of quasi-equilibrium. For these reasons, the dynamic method is more suitable when the gas-metal affinity is very high and the equilibrium time for the reaction very short. It is quick and reproducible, but might underestimate the active site concentration compared to the static systems. The dynamic method is the only analytical solution when in a chemical reaction the reactant gas molecules are in the same number of the product gas molecules, thus the pressure would not change in static systems. A point of remark: the purity of the carrier gas must be very high because the carrier flows through the sample for a long time, and the presence of impurities, like for instance oxygen in nitrogen, might change the composition of the surface metal during the chemisorption process. In a dynamic system, the choice of the probe and the carrier gas must assure the best answer of the detector if a hot wire is used. In case of a TCD, the two gases should have different thermal conductivity to have the best sensitivity of the filament response. The higher is this difference, the better is the detector sensitivity. A cold trap or a suitable adsorbent should be used to stop undesired products before the TCD, which is reliable for quantitative analysis only if we have two gases involved. Commonly used couplings are argon or nitrogen when detecting hydrogen, helium when detecting most of other gases like carbon monoxide, carbon dioxide, ammonia, etc. Carbon dioxide can be used also as a carrier gas for hydrogen. The main task of chemisorption experiments is to measure the number of gas molecules that react and are stabilized in a monolayer on the surface metal atoms or active sites. There are several methods to calculate the monolayer volume depending on the applied technique. In static technique, the most used ones are the Langmuir model the subtraction of the first and second run isotherms, followed by back extrapolation to zero pressure. The Laguerre model can be applied to isotherms type 1, and it is based on some fundamental assumptions. The adsorption energy is the same for every active site, and there are no interactions between adsorbed molecules. Adsorption is localized. The maximum adsorbed volume corresponds to a monolayer. In static chemisorption, the Laguerre can be applied to the isotherm resulting from the subtraction of the first and second run. On the subtracted isotherm, also a linear regression can be applied, finding the monolayer in the intercept. And finally, the back extrapolation to zero pressure of the linear portion of the two runs gives the total and reversible chemisorbed values. Dynamic systems provide directly the amount of irreversible gas chemisorbed because the catalyst undergoes continuously to an inner gas flow, taking off the reversible species. Once the monolayer volume is known, applying the stoichiometric factor of the reaction, we can quantify the surface active sites that were involved in the reaction. In case of supported metal catalyst, three main information can be achieved. Exposed metal surface, knowing the metal atomic cross-sectional area, the metal dispersion, knowing the total amount of metal present in the catalyst, the average metal crystallite size, knowing the metal density and applying a shape factor like a cube or an hemisphere. Static manometric technique permits to evaluate also the heat of adsorption. The isosteric heat of adsorption can be calculated by performing various analyses at different saturation temperatures in order to obtain different degrees of coverage. The analytical temperature should be chosen in a range that will not modify the surface structure. After several measurements, the average adsorption enthalpies can be calculated with respect to the isosteric heat of adsorption and the coverage degree. Other reversible effects that can be put in evidence by static manometric technique is the hydride formation occurring between hydrogen and palladium. Hydrogen literally dissolves into the palladium structure, changing the atomic distance between the metal atoms. This phenomenon is temperature and pressure dependent. At low pressure, reversible plus irreversible chemisorption takes place, but at a certain pressure, depending on the analysis temperature, hydrogen begins to dissolve into the palladium, giving place to the hydride formation. Increasing the analysis temperature shifts the flexus to higher pressures until at about 120 degrees the flexus disappears completely. The metal dispersion and surface area can be evaluated also at low temperatures, but only the first part of the isotherms before the flexus must be taken into consideration for the calculation. The characterization of some supported metals like copper or silver is quite difficult with the static manometric methods because the most used gases like hydrogen and carbon monoxide cannot give a stable chemisorption, and oxidation is disadvantaged. In these cases, a stronger oxidant is necessary like nitrous oxide. This gas is likely to release atomic oxygen and nitrogen so that the decomposition of nitrous oxide is highly favored. Static manometric technique is not applicable in this case because 1 gas mole of nitrous oxide provides 1 gas mole of nitrogen, so in a static system the pressure will not change. In this case, the dynamic technique can solve the issue, but in the carrier we will have 3 gases, helium, nitrous oxide and nitrogen. Therefore, the TCD detector in these conditions cannot be used for quantitative analysis. There are several solutions to this analytical problem. Using a mass spectrometer following masses 44 for nitrous oxide and 28 for nitrogen, or using the standard TCD but freezing the unreacted nitrous oxide with a liquid argon trap, thus detecting only the generated nitrogen. Finally, using the TCD with a prior separation of N2O from nitrogen using a short chromatographic packet column, like for instance the Porapack N. The short chromatographic packet column can be installed in the pneumatic circuit just before the analysis channel of the TCD. The column separates nitrogen from nitrous oxide, allowing the quantification of both species. Temperature program methods may be used with different objectives. Qualitatively, to fingerprint a given system, to quantify the amount of gas involved in the desorption process or in the chemical reaction, thus calculating the number of the active sites, to evaluate the reducibility and the oxidation degree of a metal, and to measure the activation energy for desorption. While temperature surface reaction and desorption involve a surface process, TPR and TPO involve bulk reactions. An adsorbed species at low temperature may remain almost indefinitely in that state. As the temperature of the sample is increased, however, there will come a point at which the thermal energy of the adsorbed species is such that one of the several things may occur. A molecular species may decompose to yield either gas phase products or other surface species. In this case, we have a surface reaction. An atomic adsorbate may react with a substrate to yield a specific surface compound or diffuse into the bulk of the underlying solid, like in case of absorption. The species may desorb from the surface and return into the gas phase, that is to say, the adsorbate is submitted to thermal desorption. The last of these options is the desorption process. In absence of a reaction, the desorbed species will generally be the same as that originally adsorbed, but this is not necessarily always the case. All samples must be pretreated before the analysis to activate the chemisorption of the probe gas molecules. Various procedures can be chosen to obtain a clean surface, eliminating undesired contaminants, to have the metals in the desired oxidation state, or to activate acid sites. After the activation, the sample can be saturated with a suitable probe gas and at a given specific temperature. Once the saturation is over, the probe gas in excess is removed by flowing an inner gas, taking off also the reversible chemisorbed gas. In case of used catalyst or when the catalyst precursors are still present, the sample preparation might be more complex. Finally, the sample is submitted to a constant rate temperature increase, and the desorption of the chemisorbed species takes place at the given temperatures. The carrier gas takes the molecules to the detector that can be a TCD, a mass spectrometer, or others. The desorption temperature is correlated to the activation energy of desorption, while the amount of desorbed gas is related to the number of active sites. Atomic or simple molecular desorption will typically be a first-order process when a simple molecule on the surface of the substrate desorbs into a gaseous form. Recombinative molecular desorption will generally be a second-order process, like in case of two hydrogen atoms on the surface desorb and form a gaseous hydrogen molecule. An important application of TPD analysis is related to the use of ammonia to characterize acid nature of some supports or catalysts like zeolites, alumina, and molecular sieve. The activation energy for desorption can be calculated by performing various TPD experiments at different temperature rates. The saturation temperature should be chosen depending on the nature of gas interaction that must be investigated. Low saturation temperatures will take into consideration also physisorbed or weakly chemisorbed ammonia. A typical process for ammonia TPD from a zeolite follows several steps. First, the zeolite must be activated, usually by degassing in inner gas flow at high temperature. Once the sample is activated, the next step is the saturation of the sample with ammonia at a given temperature. To avoid the detection of a physisorbed or weakly chemisorbed ammonia, the saturation can be performed at about 120 degrees, or alternatively, saturation can be performed at room temperature followed by a degassing phase in inner flow at about 120 degrees. Finally, the TPD analysis is performed from the saturation or degassing temperature up to 500 degrees using various temperature rates. In the example, the zeolite was saturated at 120 Celsius and several experiments at variable heating rates from 2 to 30 degrees per minute have been performed. The Kissinger method permits to calculate the activation energy for desorption that, in case of a first-order kinetics, is very close to the heat of adsorption. This equation puts in relation the peak maxima to the applied heating rate, providing in the example two distinct exit sites of different strength. The desorption of weakly chemisorbed propylamine and the surface decomposition occurring at about 300 degrees cannot be conveniently detected by a simple TCD. In this type of experiments, the use of mass spectrometer can clearly distinguish the product of decomposition. The activation energy for desorption of the integer amine can be measured by applying different heating rates and applying the Kissinger equation to the first peak only. Propylamine is desorbed by Bronsted acid sites, thus can be conveniently used in conjunction with ammonia and pyridine adsorption for a better definition of a catalyst acidity. Methanol can be conveniently used to identify and quantify the different types of surface active sites because the oxidation of methanol is site-specific. On acid sites, methanol undergoes the synthesis of dimethyl ether. On basic sites, it will dissociate into carbon monoxide and carbon dioxide, while on redox sites, it will dissociate into formaldehyde and hydrogen. The procedure using methanol is like the amine adsorption followed by temperature-programmed surface reaction. Methanol vapor is pulsed in the reactor by a dynamic system. From this experiment, we can quantify the amount of methanol vapor that has chemisorbed. The experiment proceeds with a temperature-programmed reaction at higher temperature. Usually, excess of methanol is desorbed and changed at lower temperatures, whereas the synthesis of other compounds or the dissociation takes place on the specific active sites at higher temperatures. In temperature-programmed reduction, an oxidized catalyst precursor is submitted to a linear temperature rise while a reducing gas mixture is flowed over it, usually hydrogen diluted in nitrogen or argon. In the temperature-programmed oxidation, the catalyst is in the reduced form, and it is also submitted to a temperature increase, but in this case, an oxidizing mixture of gas like oxygen and helium is flowed over the sample. TPO is often used to study catalyst regeneration when carbonaceous compounds are poisoning the active sites. TPO is less commonly used than TPR, but if the two analyses are performed in succession, making hydrogen-oxygen titration, they can provide useful information in the study of redox behavior of catalysts. The objectives of these techniques are essentially the following: find the most efficient reduction or oxidation conditions, identify the supported precursor phases, then their interaction with the support, evaluate possible regeneration procedures, characterize complex systems like bimetallic catalysts to determine the role of the second component, and establish alloy formation or other promotion effects. The reaction between a metal oxide and hydrogen produces the pure metal or intermediate oxides and water. From the thermodynamic point of view, the reduction of a solid oxide is feasible if the standard free energy change, delta G0, is negative. If delta G0 is positive, the second term of the equation must be sufficiently negative to make also negative the total delta G. In the table, we put in evidence in green lines metal oxides that can be reduced, while the other metal oxides can be reduced at higher temperatures or are not easily reducible. At cryogenic temperatures, hydrogen might physisorb on the support to be later desorbed as the temperature increases. At a certain temperature, the reduction begins on the surface of exposed metal oxide, and two mechanisms of reduction may occur, as we will see in the next slides. When reaching higher temperatures, hydrogen penetrates in the bulk of the catalyst and all the available reducible species are reduced. If the TPR proceeds to much higher temperatures, the metal begins sintering, reducing the surface area and dispersion. The reduction of a metal oxide can be described by two models, nucleation and contracting spheres. It is important to consider that the reduction mechanism can be different from the pure metal oxide and the supported metal oxide, because the metal super interaction can modify the reduction mechanism. The presence of a second metal or a dopant also can modify the mechanism. Finally, the presence of a spillover phenomenon might accelerate the reduction process thanks to the migration of atomic hydrogen through the support. In the nucleation mechanism, the reduction begins after some time and at a given temperature, often not reproducible, bringing to the formation of solid nuclei of reduced metal. During the nucleation, oxygen ions are removed from the lattice progressively, forming a solid metal, while hydrogen and oxygen molecules diffuse to the interface. Once enough nuclei are formed, the reduction process is very fast. In the example, we observe that pure copper oxide follows a nucleation mechanism, taking into consideration that supported copper might follow a different reduction profile. In the case of contracting spheres models, the reduction takes place at the surface of the oxide particle, which remains covered by an eggshell of reduced metal. The speed of reduction at the beginning of the process is very fast because it is proportional to the external available oxide surface. As the reduction proceeds, the available oxide surface of the sphere is contracting, thus the speed of reaction decreases proportionally, slowing down continuously until the metal oxide is completely reduced. The contracting sphere mechanism is generally a slower process than the nucleation. In the example, we can observe the reduction profile of a nickel supported on silica. The analytical conditions to run reduction experiments should be optimized, putting in relation the amount of reducible species with the hydrogen concentration, the flow rate, and the temperature rate. Mont Baker proposed a method to optimize the flow rate in function of the reducing gas concentration and the total available redox sites, while Mallet and Caballero proposed an empirical method to optimize also the temperature rate. Temperature program reduction profiles are often very complex to be interpreted because the peak number, the reduction temperature, and the quantity of hydrogen consumed are related to many factors. What is clear is that TPR provides a fingertip of the catalyst indicating the reduction capacity. Same metals on different supports show different profiles. The presence of other metals and dopants also change the peak size and reduction temperatures. In the next slides, we will see some of the most evident effects. Metal particle size affects the TPR spectrum. To have a clearer evidence in this profile, we run a TPR on copper 2 oxide with different particle size. The red line is relevant to small particles of about 500 microns, while the blue represents the same material but with particles of about 10 microns. In supported catalysts, usually higher metal charges lead to larger metal aggregates, and the TPR profile can put in evidence this fact. In this example, we have two catalysts made of nickel supported on silica, but two different metal percentages, 26 and 29%. By comparing the two profiles, we can see that the higher metal charge shows a more evident peak at low temperature. The support also has an important effect in redox properties. Some metal oxides used as a support generate more active sites in presence of the metal, like in this example of nickel supported on alumina, giving up to 5 different reduction peaks versus the 2 peaks in case of silica. Also, alloy formation can be put in evidence by TPR profiles. Two catalysts based on platinum and ruthenium show different TPR profiles. platinum giving 2 peaks while ruthenium 1 peak at higher temperature. By analyzing with the TPR a physical mix of the two, we obtain a TPR profile where each compound maintains its characteristic reduction temperatures. But in presence of a bimetallic catalyst with these two metals, the TPR profile changes, putting in evidence the formation of an alloy. In this example, TPR analyses are carried out on 4 catalysts containing the 5% of cobalt supported on alumina and doped with the different percentages of iridium from 0.1% to 2%. They have been prepared by wetness impregnation. There are two evidences in the TPR profile. The hydrogen consumption increases when the percentage of doping metal is increased, while the peak temperature decreases accordingly. This example is a clear demonstration that the TPR analysis offers information about the reducibility of a metallic sample and that it is possible to estimate quantitatively the effect due to the presence of a second metal or other dopants. Multimetallic systems are known for the difficulty in their characterization. An important aspect common to all the described techniques is the sample preparation. In absence of clear indications on how to prepare a catalyst, temperature program oxidation and reduction are very useful to help understanding the best way. A simple procedure is the following. First, run a TPO up to the calcination temperature to ensure that all the metal is properly oxidized. In case of used catalyst, the oxidation might remove possible carbon residuals. Then run a TPR up to the maximum temperature allowed by the instrument in use, typically 1100 degrees, to determine the complete reduction profile. This test should be done on a small amount of sample because it will not be usable anymore. Then relate the temperatures of reduction peaks, calcination, and the specific reaction for that catalyst and decide the optimal reduction temperature. And finally, run a TPR up to the chosen reduction temperature and hold for enough time for the detector signal to return to the baseline and determining this way the optimal reduction time. In this example, a supported nickel catalyst was tested according to the suggested procedure. The TPR up to 900 degrees gives a profile where the reduction begins at about 300 degrees and the peak maximum is at 450 degrees. 5 temperatures will be used as reduction conditions. T1 at 250 before the reduction begins. T2 at 300 degrees when the reduction starts. T3 at 450 degrees is the peak maximum. T4 at 470, just few degrees over the peak maximum. And finally T5 at higher temperature of 500 degrees. Reduction time was set at 2 hours, followed by 4 hours degassing at the same conditions. The catalyst divided in 5 batches was submitted at 5 dynamic chemisorptions, same analysis temperature of 25 degrees but different reduction temperatures. As we can see, the detected number of surface metal atoms, that is the metal dispersion, change in function of the activation procedure. In this case, a reduction temperature between 300 and 450 degrees provided the same dispersion. At lower temperatures, the reduction is not complete, while at higher temperature, metal sinterization begins. Finally, a mention to the use of temperature program adsorption to determine the best chemisorption temperature. The method consists in sequential analysis, pulse or static chemisorption, performed at different temperatures to define the temperature at which the catalyst interacts with the maximum amount of adsorbate. A supported platinum catalyst has been submitted to the same activation procedure, reduction at 400 degrees for 30 minutes, followed by a degassing at the same temperature for 30 minutes. Then 5 hydrogen pulse chemisorption experiments at different temperatures from 25 up to 200 Celsius have been performed. The metal dispersion calculated was plotted versus the chemisorption temperature. As it is evident, the most effective temperature for the gas-solid interaction is about 50 degrees for this catalyst. Micromeritics has one of the largest instrument portfolio for catalyst characterization. Static volumetric and dynamic techniques can be applied in a wide range of temperatures and pressures from vacuum up to 200 bar. The larger variety of reactive, corrosive gases and vapors can be used for specific chemisorption and desorption. One division of Micromeritics is dedicated to the realization of equipment for customized reactivity tests, small pilot plants, and multi-reactors for catalyst screening. I want to thank all my colleagues.
Thank you, Luca, for this very nice presentation. I'd like to open up for questions, and I have an early question for you, Luca, on BET surface area. How does that compare to the active area you presented today? So it seems like we're having a small webinar problem with audio and Luca's connection this morning. So I'll go through briefly some of the questions that we have, and hopefully I can answer some of your questions that you submitted until Luca is able to connect. So on the topic of BET surface area versus active area of the material, BET surface area is very effective for looking at total surface area of the materials versus these heterogeneous catalysts where we have active surface area. So these are very specific probes when we're comparing the two. A typical material could have 10 or 100 times more total surface area versus active surface area if you consider highly dispersed systems such as platinum on alumina or palladium on alumina. So BET surface area generally is much larger than active surface area. So the two of them are quite complementary. To understand the total material and total area, we use BET, and then comparing that to the active area, we can use that for specific metals to understand interactions with those highly active sites. A second question that we've received, what's the benefit of static versus dynamic chemisorption? Earlier in the presentation, it was really very clear. Static chemisorption gives the benefit of looking at total quantity chemisorbed, and that can be both for strongly bound or irreversible adsorption and also reversible adsorption. So by changing the active concentration, the irreversible stays on the surface in these strongly bound sites versus the repeatable amount, which by simply changing concentration, we can have more or less adsorbed on the surface. We can contrast that with dynamic chemisorption, where dynamic chemisorption specifically addresses strong or irreversible chemisorption. So active sites are populated. It's a titrating technique, so small injections are performed, and then inert gas will purge away any reversible amount that's adsorbed on the surface. We have another nice user question on what are the experimental parameters that may cause sintering on materials. Specifically, if we have an active metal that is supported on an oxide surface, what parameters can cause sintering?
Hello, Jeff, can you hear me?
Yes, we can hear you very well, Luca. Thank you.
Okay, sorry, but I don't know. We had a problem with the computer microphone connection, so I'm using the telephone now.
Okay, so I'll repeat the question for you, Luca. What experimental parameters can cause sintering?
Hello? Sorry, Jeff, can you repeat the question?
Yes. One attendee asks, what experimental parameters can cause sintering of the materials?
Okay. The sinterization is, let's say, a process that usually takes place at a high temperature, or if we stay at high temperature for a long time. Usually, any catalyst is produced by a calcination process, that is an oxidation at high temperature, depending on the support mainly and on the metal. That will fix the metal salt on the surface and in the back of the support. So usually it is a good procedure not to overtake the calcination temperature, because if we, for instance, calcinate a catalyst at 500 degrees for a certain time, means that the metal aggregates are stabilized, are stable at that temperature, and will not change if we stay below that temperature. But if during the process we can overtake the calcination temperature, then the mobility of metal atoms increases, and the metal atoms can move and forming larger aggregates. And once the larger aggregates are formed, usually this phenomenon is irreversible. So we can't go back to the original metal dispersion.
Okay. You had presented very nicely this data on palladium as chemisorption and the formation of the hydride. Can we distinguish between what's on the surface versus the hydride when palladium is present?
So in this type of experiment, what we see is, depending on the temperature, we have normally we have to use a static volumetric manometric technique to put in evidence this effect. So at low pressure, depending on the temperature, usually the gas begins to chemisorb in a reversible plus irreversible way. And then at a certain pressure that is function of the temperature, the hydrogen begins to be dissolved into the bulk of palladium. And this process is relatively quick, but consumed a lot of hydrogen. When the dissolution, or when palladium reaches the maximum capacity for hydrogen dissolution, then the isotope proceeds flat until any pressure. So when we dissolve the gas in a static manometric by applying vacuum, we remove both species. We remove the reversible chemisorption and also the hydrogen that was dissolved into the bulk. So when we apply the difference between the two isotopes, we get only the irreversible hydrogen. But if we need to calculate the metal dispersion for only the strong interactions, so the irreversible, we need to apply at the first part of the isotope, at low pressure, because at low pressure, the dissolution of hydrogen does not take place. In case of dynamic technique, this is not possible, because we have a certain, when we push a gas into the gas stream, the pressure is usually atmospheric pressure. So we already overtake the pressure at which hydrogen dissolves into the bulk. But being the catalyst always under a continuous flow of inner carrier, the inner carrier will remove at the same time the reversible hydrogen and the dissolved hydrogen into the bulk.
Luca, you mentioned several probes, several methods for acid sites. What's the benefit of using simple adsorption like ammonia or pyridine versus a temperature program reaction?
Let's say normally they can be performed in sequence if using a dynamic system. And when we just run the adsorption of these gases, okay, first of all, ammonia can determine the complete acidity, as I mentioned in the presentation, and by running more static manometric analysis at different temperatures, and also having starting from very low pressure, we can evaluate not only the number of the total active sites in function of the temperature, but we can also calculate the isosteric heat of adsorption. And we can put in relation the isosteric heat of adsorption with the coverage degree, because let's say the heat of adsorption is higher at low coverage, so at the beginning of the chemisorption. When we reach the saturation, normally the heat of adsorption becomes very low. So we can find this relationship in case of static manometric technique with both pyridine and ammonia. When we use the dynamic technique, we can evaluate the amount of gas chemisorbed by pulsing the ammonia or pyridine into the microreactor, and then we can run several temperature program desorption techniques. Here we have to take into consideration that if it is very important the temperature at which we do the saturation or the chemisorption, because depending on the temperature, we can also put in evidence at low temperatures the physisorbed effect. So when we run the TPD, then usually we want to evaluate the energy of adsorption only of the strong acid site. And therefore, it is better to saturate the sample at around 100, 120 degrees, where the physisorbed ammonia is automatically removed by the carrier flow. When running then multiple TPD experiments, we can put in evidence with the different temperature range the activation energy for desorption. Now for ammonia, ammonia is dissolved molecularly. So it's first order kinetic, follows as first order kinetic. So we can evaluate easily the activation energy for desorption, and thus calculating also the adsorption enthalpy, putting in evidence different type of acid sites on a zeolite or an acid sample. And the same with pyridine. Pyridine, the difference with pyridine is that it will not, due to the dimension of the molecule, it will not be allowed to enter in smaller micropores that usually are not effective for a chemical reaction for zeolites because they are too small. And so it is important to evaluate only the acidity of a catalyst that is effective for the chemical reaction.
Okay. So this next question goes back to metallic catalysts. And for bimetallic systems, such as platinum tin or platinum rhenium, what's the best way to characterize these? And what's a recommended gas for adsorption for trying to obtain dispersion on these materials?
Okay, so the type of gas and the analytical conditions sometimes are not so easy to be determined. First of all, I always do a literature search to see what has been already done by other laboratories to have some clues to analyze a catalyst. The second thing is that it is very difficult to give an interpretation to the results, only having a bimetallic catalyst, only one sample. I mean, what is important, as I have shown in a couple of examples, is to create let's say, bimetallic or multimetallic component by changing the percentage of the metal or of the dopants, and running TPR experiments and chemisorption on the different catalysts to see which is the effect of the dopant percentage into the catalyst to give a better interpretation of the metal dispersion and TPR profiles. Now, for what regards the metal dispersion, it is difficult to understand exactly where a molecule like hydrogen or carbon monoxide will be chemisorbed is more likely to chemisorb on one of the metal or on the promoter. So it is better so the bimetallic or multimetallic catalysts are very complicated to be tested, and we should have available several catalysts with several or increasing amount of dopants or second metal to see which is the effect on chemisorption, and so the amount of gas chemisorbed, and also to the TPR/TPO profile. But bimetallic or multimetallic catalysts are not so easy to give an interpretation. Also, the support can influence a lot the chemisorption amount, the chemisorption quantity, and the TPR and TPO profiles. Therefore, it is very often a common procedure to prepare a bimetallic catalyst with variable percentages, or maybe a monometallic catalyst, but over several supports.
Okay. This next question is also similar for supported nickel oxide catalysts. What method do you recommend? Static chemisorption or dynamic chemisorption?
So for nickel catalysts, usually they can be well analyzed by hydrogen chemisorption. In the example I have reported, it was a static in one example and the dynamic in the other example. Let's say the choice of the static or dynamic technique depends, first of all, of which type of information we need, and second, also because as we have seen, chemisorption can give reversible plus irreversible gas chemisorbed, and especially the other important parameter in the choice of one of the two techniques is the equilibrium time. Because when we run static volumetric or static manometric chemisorption, we give time to the system to reach the real equilibrium between the gaseous phase and the adsorbed phase at that pressure and at that temperature. While in a dynamic, the only way we have to control the contact time between the gas pools and the metal is the flow rate. So we have to keep the flow rate as low as possible to improve the contact time, so reaching a situation of almost the equilibrium. For instance, it is not possible to use or is not advisable to use the dynamic technique of using hydrogen on ruthenium, because ruthenium gives a spillover effect even at room temperature, and therefore the equilibrium time is extremely long. And all the tests done with nitrogen and ruthenium always underestimate the metal surface area and dispersion for this catalyst compared to the static manometric technique. In case of nickel, normally hydrogen can be used to characterize nickel, also because a carbon monoxide might give some carbonyl compound on the surface, making much more complex the interpretation of the results, because the stoichiometry is not certain. While with hydrogen, there are no problem in the stoichiometric factors, because hydrogen adsorbs in a dissociative way.
So the next question is also related to supported metals. For the materials palladium on carbon or palladium on alumina, is there a preference for CO chemisorption versus hydrogen chemisorption, and anything that we should be worried about when using either CO or hydrogen with these materials?
So palladium can be analyzed easily with hydrogen and also with the carbon monoxide. With the carbon monoxide, but usually I would not compare the dispersion and the metal surface area. Why? Because with the CO, the stoichiometry is not completely known, because it depends on the temperature, the surface temperature, the pressure, and so on. While with hydrogen, we have to use a low pressure for the determination of the reversible and irreversible chemisorption, and so the metal surface area. In addition, palladium has we have to also take into consideration the support. Because when we have carbon, depending on the type of carbon, hydrogen might also have an interaction with the support itself, especially if we have a microporous carbon. In addition, the supporting any metal and also palladium on carbon makes some problems in let's say sample preparation, because carbon cannot be used or cannot be submitted to temperatures that are too high, and because we risk to modify the structure of the support in this case. The lucky thing is that palladium has not such a high, palladium oxide, such high reduction temperature. Usually it is about 200 degrees or less, and therefore we can easily reduce the catalyst, even in case the support is carbon. But with palladium, I would say we can use hydrogen, knowing that we have, in case of carbon support, we can have an interaction of hydrogen with the support, and then we need to use only the first part of the isotherm, or at least increasing a little bit the temperature to shift the flexus that is indicative of the dissolution of hydrogen into the bulk at higher temperature, so that we can have a better definition of the first part of the isotherm. If we use carbon monoxide, we should consider just the amount of gas chemisorbed, because if we calculate the metal dispersion and the metal surface area, and the stoichiometry is not well known, we cannot compare then the results with hydrogen chemisorption, of course. And the other thing is that if we need to compare the two results, also we should do the experiment at the same temperature, because as we know, as we have seen in the temperature program adsorption, the amount of gas chemisorbed is also a function of the temperature. So if we need to compare chemisorption of hydrogen or carbon monoxide on any catalyst, we should perform the experiment at the same temperature.
Luca, we have many questions this morning, and we've run over on time, so this will be the final question for this morning. Is the heating rate during activation, can that affect the catalyst performance?
Yes. Yes, especially with some catalyst that has a surface mobility of the metal atoms. Usually, also the heating rate might affect the mobility of metal atoms, giving as a result the sinterization. For some, especially for instance copper, so it is recommended usually to use the lowest heating rate possible to avoid the sinterization of the metal. So heating rate for some metals is very important. In other cases, the heating rate should be chosen, especially for TPR or when we do the reduction, according to a rate that should assure the complete reduction of the catalyst. But in many cases, heating rate is important and can improve the mobility of metal atoms by promoting a sinterization effect. That's the catalyst after the heating rate is no more is different from the original one.
Thank you, everyone, for attending today. Luca, do you have any concluding remarks or anything you'd like to add for today's presentation?
No, not really. I would say that the world of catalyst is very challenging, research field, and let's say usually a single technique provide very limited piece of information, and we should combine several techniques to better understand the behavior of a catalyst, especially when studying catalysts after a chemical reaction that are submitted to phenomena like poisoning or fouling, and to study the regeneration effect and so on. And so it's a complex matter, very challenging, and also I want to thank many customers. We are finding very interesting results and unexpected results. So even after many years working in this field, every day I would say that I learn something more. Okay, thank you for your attention.
Great, thank you, Luca, and thank you to everyone for participating in today's webinar. We hope you find it useful and beneficial. Please don't forget to check back for upcoming webinars on micromeritics.com/webinars. We hope to see you all again very soon. Please take a few minutes to fill out the survey at the end of the webinar. Once again, thank you and have a great day.
Thank you, Jess.